I mean, computer scientists are pretty amazing, right? I have an iPhone that is so much more amazing than my first computer that I could actually literally take apart. I cannot take apart an iPhone.
They can't put together a nitrogenase molecule.
Yeah, so my group works on superconducting qubits, and I think many of you this weekend will probably program a superconducting quantum computer, a small one, from IBM using Qiskit. And so these superconducting qubits are basically electrical circuits. They're resonators. And the one feature of them, though, is that when you cool them down to very low temperatures, they sort of behave like atoms in the sense that they have discrete energy levels. So they're quantum mechanical. And of course, in quantum computing, we tend to use the ground state and the first excited state. We call that a qubit. What my group's working on primarily, I'd say, are a couple directions. One is, why doesn't that thing work better? What's preventing it from being like a natural atom? Like, you know, Ike works with natural atoms, ions, and they have lifetimes that are so long, you know, hours, maybe, even longer. But our superconducting circuits, their lifetimes are maybe 100 microseconds. What's limiting that? Why can't it be longer? Well, we've solved many of those problems over the years. We have more to go. 20 years ago, it was a nanosecond. And today, it's 100 microseconds or more. And it comes down to materials, fabrication, how you design that circuit. It all matters, as you might imagine. Everything matters. So one thrust of the group is trying to make these qubits better and better and better, because if they have higher coherence, that tends to lead to higher fidelity, and that's really what you want. It's how many of these gates can I apply to my quantum computer before it starts to fall apart and lose the quantum information. The second part of the group focuses on larger circuits. Like, we have a 16-qubit chip, 21-qubit chip, and what we're trying to do there is study entanglement, primarily, manifestations of entanglement. How does entanglement start? How does it propagate? When it propagates, how do I benchmark that complicated entanglement state? Sometimes people call it many-body localization or many-body entanglement. I don't know that we have many bodies yet. Maybe FBE is better, few-body entanglements. It's 16, 20, something like that. But even at that scale, it's very complicated to understand how it's working and how to benchmark. It's very expensive, as you'd imagine, because one of the hallmarks of quantum computing is that as you increase the number of qubits, it gets exponentially more complex, exponentially larger state space. And so benchmarking even 16 or 20 qubits, while possible, is very, very challenging. Yeah, so those are the kinds of research directions we do. Maybe the last thing that's interesting, and a recent paper we had, was we coupled a superconducting molecule, so 2 qubits that were entangled, to a waveguide. And based on the entanglement we created, we could have that artificial molecule emit a photon to the left, by choice, or to the right, by choice. And in the jargon of the field, we'd say this is chiral. It's a chiral or directional photon emission. The reason that's interesting is if we didn't play that trick and the photons just emitted, it actually goes in both directions until we detect it and then you resolve it. But it's 50-50 which way it goes. But by being able to choose which direction it goes, we can now connect modules, small-scale processors, together, processor A to processor B, or let's do processor C instead, just by choosing which way the photon goes. And so that's a recent paper that we just had. And now we're working on catching the photon. We know how to emit it, now we want to catch it.
I'm curious, based on your last question, how many of you here are here because you're inspired by doing a cool science project with quantum computing? How many of you are here because you're inspired by making quantum computers useful for mankind to solve problems like the excited state of nitrogenase? Actually, it's about half-half, or maybe the second half was shy about answering that question after Donna. But Will, you mentioned these IBM processors that are based on what you've built.
Yeah.
How will these folks in the audience be able to tell this weekend whether IBM's actually letting them use their processor or if they're simulating with them with a classical computer behind the scenes?
Well, that's a really good question. I think you set a bit, and which way you set it, 0 or 1, it's going to send it to either the simulator or the quantum computer. But you could do benchmarking yourself, and I would encourage you to do that, is benchmark your quantum computers, right? And you can run your algorithm, whatever it is. Algorithm could be generic, it doesn't have to be solving a specific problem. A sequence of gates is an algorithm, and you could benchmark that quantum computer and look for the reality that you get out. A real quantum computer is going to have errors, and you will see those errors.
You're saying the real quantum computer sucks compared with the classical computer?
Well, I didn't quite go that far, but the real quantum computer today, if you look at IBM's quantum computers, which are at the forefront or close to the forefront, they have what's known as quantum volumes, and basically what that is how many qubits can I run for how many steps? And there's an algorithm that does that, but it's basically, can I do 3 qubits for 3 steps before I lose it, 4 qubits for 4 steps, 5 for 5, et cetera. And whatever that number is, that's your quantum volume. And to make it sound bigger, they'll take 2 to that number, so 2 to the 5th or 2 to the 6th. And the quantum volumes today are around 7 or 8 qubits. I can run 7 qubits for a depth of 7 gates. And on the one hand, you'd say, I wish I had more, because we want to have more, right? And that's what research I'm doing and many others is let's make those qubits better so we can get more. On the other hand, from the perspective of someone who's been in the field for 20 years, I'd say, wow, that's pretty darn good, because I remember when we started, it wasn't even 1. It was probably 0. So you will use, this is, I think, very exciting, is that you're going to use a quantum computer, a small-scale quantum computer, whether it's IBM's or IonQ's or whoever's it is. You're here at the very beginning, right? We're just getting to the point where we can really online access a quantum computer, run an algorithm, get some results out, compare it to what the simulator told us we should get. And for many of the algorithms you write, you'll see that those line up, right? To answer your question though, like, how do you tell the difference? Let's say that the quantum volume is 7. Try 10, because the simulator will tell you what that answer is for 10, and it will be the answer to the problem you're posing or trying to solve. But on the real quantum computer, it won't look as good. And the more complexity you add, either more qubits or more depth, the less and less it will look like that simulated result.
Sadly today, but maybe it'll change. Maybe that's why you're here, because there's hope for better in the future.
Indeed.
But not quite yet.
Not yet. But we can do real things. We can have hackathons.
And we can do really awesome science today, but not quite yet do something useful.
Or commercial, maybe.
Commercially useful.
Yes,
That
indeed.
sounds like a great segue to Sloan School.
I don't think we can reorder things that much. Quantum matrices, when you multiply them in different ways, they give different results.
Okay, I will take the privilege of being elderly to skip and come back at the end.
Well, that hierarchy sounds right to me, that you can pull rank. At the research group, the IDE, the Initiative of Digital Economy, we look at all kinds of technologies and how they impact the economy. But one way to think about this is around timescales, because when we're looking at technologies that have been out there for quite a while, we could look at how they're impacting the total economy. So not just even the US economy, but global trade and lots of other nations. So if you look at the silicon chip revolution, that's out there everywhere, and we can see it in productivity, and we can see it in labor markets, and we can see it possibly even in things like inequality in the economy. And there are a lot of other very interesting technologies that are so well deployed across the total economy that that's the aperture that we look at them. But something like quantum computing is not in the economy today. It has no measurable impact whatsoever. So what lens are we going to use to have a look at this? Obviously, it raises a whole bunch of very different questions and very different things that we should be looking at. We try to add as much precision as we can to the discussion. We think that's important here at